Hello, everybody. This is Mr. Shrum, and I just wanted to walk through this intro to biology tutorial just to see if I can add anything to these slides and walk you through some stuff. This is Intro to Bio. Our objective: use the scientific method to investigate a biology question. Tutorial, blah, 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 scientific inquiry, lesson, scientifically thinking, summary. All right, so warm-up question, everybody. What opinions do teenagers have about vaccines? Do hand sanitizer decrease a person's risk of a bacterial infection? Is buying organic food an ethical choice? How hard is it for people to reduce stress in their lives? Okay, so given these questions, this is the one that can be tested, measured. Opinions, you can't really test those. Measure, no. Ethics, oh boy, that's touchy subject right there. So you can't test it, measure it. How hard is it for people to, yeah, you can't test that because everyone has a very subjective view about opinions, ethics, and how hard it is for them to reduce their own stress in their lives. So what may seem hard to one person may seem easy to one. But here we can measure that. So that is what we stick to in science. Tested, measured, measurable data, one of those. So in this question, 2 students are planning an experiment that will test how planaria, aquatic flatworms, respond to different environments. They will conduct 2 investigations. One of them tests the worm's responses to different water temperatures. The other is seeing how they respond to different levels of acidity. So temperature in one, acidity levels in another. So the first student is like, hey, let's buy 2 groups of flatworms and use a different group for each investigation. But student 2 is like, wait, hold on, dude. Shouldn't we actually use the same group of worms? It doesn't make sense to use 2 different groups because how do you know that the difference isn't between the different groups and not the actual things we're trying to measure, which is temperature and acidity? So which do you think is actually the best way to go about something? Why or why not? Explain, and we'll look into this further. You can watch this video on your own. I'll just skip it for now. The scientific inquiry. You've probably taken some science classes. I mean, you're taking one right now. But have you ever thought about what science means, right? What makes science science and other stuff not exactly science? Science is the investigation of the natural universe. And specifically, biology is the branch that studies living things and the environments they live in. Biologists, like all scientists, use the scientific method. And boy, scientists love this scientific method. It is like their bare bones, most essential tool that they will always use. And scientists have always used this method. And it's probably going to be the best takeaway from your science classes. If you don't remember anything, remember this method, because we use it in our day-to-day lives to some degree. But this is the cornerstone, the most important part of science. This is a process. And if you use this process again and again, as humans have throughout all of the ages, make observations, ask questions, make predictions, construct a hypothesis, test that hypothesis with an experiment, look at the results, what can you conclude from the results, and then tell other people about your results. And that's it. It seems simple, and to some degree it is simple, but perhaps the experiments that you need to conduct are very technical and difficult. But the process itself remains simple. You look at the world around you, you get curious, you're like, hey, I wonder how that works. You make a prediction about what will happen if you conduct an experiment, design an experiment that appropriately tests your prediction, and then once you repeat that again and again, you can make a conclusion, publish it in a scientific journal, tell your friends, family, anyone that will listen, right? And communicate your results. And then they can test it. And the more people test a hypothesis, the stronger the argument and conclusion becomes. Okay? Okay. But first and foremost, observations. Looking at the world around us, we are given 5 major senses for the most part: sight, taste, touch, sound, smell. Using these senses, we observe the natural world around us. And then we can start inferring about the world around us. What can explain certain things? Using past evidence and observations, what can we infer? And in this example, observation is the origin of all inquiries. They may observe the sky, wonder why it's blue. I know I have, especially when I was a kid. And that prompted scientists to conduct scientific investigations. And today, we now know that it's blue because of the scattering effects of sunlight on the tiny little molecules in our atmosphere. Okay? So sunlight enters our atmosphere. These molecules scatter the light. And when light is scattered, it appears blue to our eyes. Okay? So curiosity, big part of science. This gives a coffee example. A medical researcher observes that people experience an increase in blood pressure after consuming coffee. Do you guys drink coffee yet? Is that a high school? Yeah, no, I drank coffee in high school. I don't know what I'm talking about. Elevated blood pressure. I love caffeine. Coffee contains caffeine, a compound that stimulates the nervous system. If you've heard of a stimulant, caffeine, technically a stimulant. It excites the nervous system. After analyzing past studies, the researcher infers that increased blood pressure seems to increase the risk of heart disease. So she wonders if heavy coffee drinkers face the same risk because of regular spikes in blood pressure caused by caffeine. So observation led to questions. And that prompts these types of scientific questions. And that will help you narrow in what you're trying to look at. And the more you ask, the more you're going to learn about the subject of interest. And these questions tend to be very practical, empirical, dealing with numbers and data. Quantitative data is measurable. Think of how long a football field is, or how much a box weighs, or how much coffee is in a mug, right? You can measure it. Qualitative data is something that can't be measured, but it can change over time. So, oh, sorry about that. The color of the sky or the texture of coffee grounds when they're dry versus wet are both qualitative data. So if you can observe changes in it, but you can't necessarily measure it, that's qualitative. Oh, okay, interesting graphic. Major coffee countries and their consumption rates. So America, according to this graph, pretty high coffee drinkers. Germany as well. Japan actually surprises me. Italy, no, I definitely think of European as coffee. I'm surprised I don't see any South American countries on here, because I know a lot of coffee beans are grown in that region. But the United Kingdom, typically known as tea drinkers for the most part, but I thought Japan also drank a lot of tea. Maybe that's the Americanized Japan, right? More coffee drinking. I don't know. There's a story there. See, I'm asking questions. Look at that. I'm sciencing. But a scientific inquiry can't answer questions about a person's belief, ethics, opinions, feelings. Yeah. This stuff is hard to deal with in an objective sense, right? What someone believes, their ethics, opinions, and feelings, it's very personal, and science can't necessarily delve into those questions, as well as the more data-oriented questions. But here are some of the examples that are good questions for science. And here are those that science cannot take these on. It's just, science is limited in that way. It can only help us measure our natural world, not the world inside of our head, our ethical realm of what we should and shouldn't do. That's for us to determine. Sorry, had to get deep, existential almost. Now let's explore how the medical researcher framed the question. So remember, coffee, high blood pressure. Does this lead to a higher risk of disease, heart disease? Let's see. She can try to answer this question using both quantitative, measurable data, and qualitative data. So what's the quantitative data? Well, you can measure the blood pressure, and that's quantitative. The qualitative data will consist of images. So they're going to take pictures of their hearts. And then if you notice a change over time, even though you can't measure it, but you can see the difference, that counts as data. So, the more she looks into this, these are questions that she can't answer with this data. How do they feel? Are they worried? Are manufacturers responsible? So that's just no. Like, this is not for her to pursue. So once you observe, once you ask questions, you're going to construct hypothesis. One hypothesis. If you're constructing plural, that's hypotheses, getting technical. But all you need to remember is that this is a prediction, an educated guess. And based on the experiment, you're testing the hypothesis and whether it is supported or rejected. So we'll get into that. Does drinking coffee increase blood pressure? So this is the question. Now she has to make an educated guess, a prediction, based on her information already gathered. So she may use this as a hypothesis. Drinking more than 5 cups of coffee a day increases blood pressure, causing an increase in heart disease across the lifespan. So she's predicting her study will show that heart disease is more common among heavy coffee drinkers than among non-coffee drinkers. So one question I'm wondering is how she determines heavy coffee drinkers. Like, what's heavy to her? And she will have to define those terms. In experiments, there are several things that can affect the outcome. These are known as factors, and these factors are called variables. We refer to them as variables. And they can be either independent, I-N-D-E-P-E-N-D-E-N-T, independent, and dependent. So if they're independent, this is the variable that scientists control. And this is the one they're interested in seeing what it does in the experiment. There should only be one, ideally, looking only at one variable at a time. If it's dependent variables, these are changed and affected by the changing independent variable. So the independent variable in the example is the amount of coffee a person consumes. The dependent variable is the change in the heart. So the changes in the heart and blood pressure depend on this other variable that is changing, okay? So that is the relationship between the two. Here are some tips, okay, to consider when you're conducting studies. Outside factors, you got to control these as much as possible to get the best result. So in this example, plant growth, these are all the factors that can affect. And if you're looking at one, such as the amount of water, and that becomes the independent variable, then all this other stuff has to be controlled. And you have to find a way to make that possible, to do a sufficient experiment. Another factor, groups in a study. So when researchers have an experimental group, and you also have a control group, and a control group is just a group that is not tested on. Kind of like this very average group that is your base level. And you see how the experimental group is different from this control group. Okay. So comparing groups is where scientists can observe the changes. And recording data as accurately as possible is very important. Because if you record data and it's inaccurate, you're kind of out of luck. Like you wasted your time. And no one likes to waste their time. I don't. Sample size. Yeah, we'll get into sample size a bit later. Some people find this a little confusing, but a sample size is the number of people researchers include in a study. The larger is usually preferred because it's often more representative of the population. However, there are times when it may be too expensive to get as many people as possible. So you can find a certain number of people that you can use, and you know that it will be still accurate. Because you can't test everyone on the planet. There are billions of people. Some people speak languages that no one understands, so it would be hard to communicate with them. It would just be a very big, expensive endeavor, very accurate. However, there are just limitations to what you can do in the real world. But in this example, the researcher wants to study two groups. So we got the coffee drinkers and the non-coffee drinkers. So yeah, interesting looking bunch here. Also interesting. Yeah. So she wants to study them for 15 years and monitor their risk for heart disease. And she implements these factors. She starts with a large sample size, 10,000. So that is a pretty good size. She chooses people in the same age group. That's good because people at certain ages are more prone to heart problems and heart disease. These people have no current medical issues and have a healthy body weight. So age and body weight are known risk factors, so she's trying to control those. And she divides them into male and female to control that difference, apparently. Interesting. So she interviews them before, talks about their past, their medical history, and if they have a history of heart disease outside of coffee consumption, she will not ask them to be in the experiment. Because if your family has history, it's more likely that you're going to have that, and you could mess with the results, because that's regardless of coffee consumption. So she screens both groups to test their blood pressure, takes pictures of their heart and circulatory systems, and she does this 15 years. That's a long time, but these long-term experiments can be very useful. And another thing with these long studies, maybe people don't want to stay in the study for 15 years. 5 years later, they're like, yeah, I don't want to drink coffee anymore, but that can mess up this study, so can I leave? And she'll try to offer them reasons to stay, like money. People like money for the most part. So in medical research, it's important to note that some factors you're just not going to be able to control. And that's okay as long as you communicate that. In the case of human subjects, certain factors can't be regulated because, like I said, cost earlier, time, and ethical considerations. Yeah, so you can't intentionally hurt people. That's wrong in my opinion and in most people's opinion. However, people test on animals, which is unethical in my opinion, and I think that's becoming more accepted that we shouldn't test on animals because there is an ethical dilemma in there. But then you get into like, okay, well, then how do we test these things? And that's where it gets a little complicated. But anyway, moving on. The coffee researcher conducts interviews to learn the medical history of the participants and their families. Sometimes people are not accurate, or they'll say that they don't have a history, where in fact their family does have a history, and maybe their families just weren't very vocal about it and they didn't know. And that's not necessarily their fault, but that does lead to inaccurate information sometimes. And in here, she considered factors such as age, gender, weight, but she didn't take into account other factors like smoking habits, what they ate. That can be a big issue for some. And considering all of the other factors, that would probably bring the sample size down. And as large a sample size as necessary and possible is usually the better. Repeat, retesting, doing it again and again reduces the possibility of errors. If one experiment goes wrong and you get weird results, if you do it again and again, that's okay. You'll eventually narrow down the results and begin to see the repeated analysis. So if a repeated experimentation supports a hypothesis over a long period of time, it becomes a theory, a scientific theory. A scientific law is a principle that's been confirmed by repeated experimental observation, while a theory is a well-supported explanation. It's key to remember the difference here. A law is how something happens, while a theory is why something happens, okay? There are very few laws, straight up laws. They're usually physics-based, and you can observe them for the most part in the natural world. Gravity, we refer to that as a law of gravity. We know that when we drop an object, gravity will pull it to the ground. That's a law because it's happening. That's how it happens. Now, to explain why this happens this way, that's the theory. So a theory can describe a law, right? But a law is just the thing that happens. The theory tries to explain why it happens. Okay, and then over here you see the first Newton law. Forces are balanced. One object is at rest, stays at rest. Objects in motion stay in motion. Okay, the sum of all forces equals 0. derivative, the change in velocity, which is acceleration, is equal to 0. A equals 0. Yes. I hope you all know the Newton laws. In some cases, repeated trials with the same group aren't possible. So the subjects will age 15 years by the time the study ends. However, the researcher can repeat the study with a different population in other locations around the country to see if she gets similar results. So you can see some experiments need a lot of planning and preparation. And once you get the results, you're able to make a conclude. The conclusions drawn should answer these questions. Do the results support the hypotheses? What happened? How can the results be explained? And what are the recommendations for future research? So, was your prediction supported by the experiment, or did it not get supported? Did you have to reject your prediction? What happened in the experiment? It should explain what went down. How can you explain it? Why did the results come out the way they did? And then if people want to make their own hypotheses, predictions, and design their own experiments in this subject area, what do you recommend? So this is generally the way journals, scientific journals are written, and the analysis, results, conclusion sections. This is the questions they go for. So, the researcher established there was no significant difference in heart disease risk between coffee drinkers and non-coffee drinkers. That's good to know because I drink coffee and it's great, but some of my friends do not think so. So she has to conclude that her hypothesis is unsupported, and she has to reject the hypothesis. You'll hear that. Reject the hypothesis, or you cannot. We'll get into that. That's more like a college level null hypothesis versus your hypothesis, and whether you can reject the null hypothesis. Yeah. But for this class, what we can say is your prediction supported or not supported? Okay. That's the easiest way to think about it. At this moment in time, the researcher found that both groups suffered from an increased risk of heart disease with age. But it wasn't higher in the coffee drinkers case. So, like we said earlier, you can further test by doing similar studies that control other factors like diet, like ethnicity, or your mixed background, stuff of those sorts. And here's another big part of science is the collaboration, the collective observations of the natural world. Repeating and modifying experiments help us all better understand the world around us. Like I said, scientific journals, that's one of the more established way to communicate with other scientists in your field. This researcher had a seminar, which is like a little presentation room area where scientists talk to each other and talk about their studies, the experiments, what happened, what trouble they had, what they can learn, and what they would do differently in the future. So in this activity, it asks you to plan an investigation using the scientific method to answer the proposed questions. Ask you about observations, inferences, scientific question, construct at least 2 possible hypotheses, and then out of the ones you chose, pick the best one you want to make a prediction with. And then how would you design your experiment and explain your independent variable, the variable you want to change, and the dependent variable is what you're going to look for a change in by changing this other variable. And how are you going to control for outside factors? And then analyzing and communicating your results. How are you going to do that? So this is like your own little experiment lesson activity. I'll let you do that. Don't think about it too hard. It's kind of like what we just went through with the coffee, but you get to do your own, you get to design it on your own terms. Thinking scientifically, skeptic. I'm sure you've heard that word used a lot. Maybe in a negative way, at least not in the most positive way. But in science, skepticism is a great attitude to have. You always want to double check before you just accept statements as fact. You generally want to investigate and see if the evidence does support the things people are stating. Because people can be biased, right? And they may have flaws in their studies. And it is a good idea to double check. And it's not, you're not being rude or offensive if you want to double check, right? That's okay. Thinking critically. So using past knowledge and new information, you got to look at every piece of information you can get. And looking at flaws or designing new studies that avoid these flaws and find solutions to real life problems. The more research, the more you can confirm facts. You will detect flaws or gaps in the current evidence in your area of interest. Prior knowledge can help you analyze problems and questions currently. And then looking at solutions, you can develop other solutions to other problems, okay? So being skeptical, critical, you really want to make sure you're doing the best you possibly can. This has a video, and it asks you, can you identify how Dr. Collins is using critical thinking? You know, why is he solving problems? Is he looking for flaws? How is he How's he doing that? And here's a sample answer if you need to look at that. Yeah, you can pause or look it up. Cool. Accurate measurements. Yeah. So science deals with measuring data, and you want to be as accurate as possible. And like for blood pressure, this a cuff, blood pressure cuff, if it's malfunctioning, it could give you consistently bad results, and that's not accurate. So we don't want that. We got to make sure everything's working correctly and measuring accurately. Validity is the precision with which equipment or a test measures what it is intended to measure. A valid test is an accurate test. So it's a good way to think about this. Validity is the precision. So is a piece of equipment measuring what it's measuring? And then a valid test is it measures that thing correctly. So is a tool designed to measure blood pressure measuring blood pressure? Yes, then it's validity. And a valid test is accurate. So you want to know that it's testing what you want to test reliably, you know? Yeah, a reliable or valid test it consistently detects the disease in the majority of them. Yeah. So reliable is a keyword for valid. And it's important to remember that there's always a little bit of error in everything you do. Technical errors, human errors, errors caused by changes in environmental conditions, and that leads to inconsistent results. And your conclusions may be inaccurate if you're given inaccurate measurements. So you use percent error to calculate the difference of the accepted value and the experimental value. Percent error equals the experimental value minus the accepted value over the accepted value times 100. So in this question, we can see a group of students measured the temperature at which various substances boiled. Their results are listed in the table. So seawater, mercury, jet fuel, ethanol, which is another word for alcohol. Here's the accepted value. So this is like what we know beforehand. And this is what we measured in lab. So you can see there's a little bit of difference between the two. But which one has the highest percent error? Can you guys, yeah, okay. Here's the, I was going to pull up the whiteboard, but here we go. So percent error, you'll take the experimental value, this number for each one, minus this number, divided by this number, times 100. So for ethanol, we have the experimental value of 81.8 minus the accepted value, 78.4, divided by 78.4 times 100. So that's 4.3%. And that was the highest of the others. And percent error is more important than the difference between, because I'm sure some people are like, oh, that's like the biggest difference, but it's also just overall higher in general. So you don't want to go off of just pure difference. You want the percent difference in error. So remember that. Remember that. It's the most accurate way to look at things. Bias. That's a good word. Science doesn't show bias, but people, humans, flawed, crazy people, they have bias, even if they don't know it sometimes. So if a company performs a study, they have an interest in making the study look good for their products, right? So it would be less biased for someone else to do an experiment about the company product that has nothing to do with the company, right? Because if a company is giving you money to do an experiment, chances are you're going to make some adjustments to the experiment to make it look better for them. They might also show bias so they can publish their results in a scientific journal. Yeah, so scientists may change data or maybe lead to not so accurate experiments just to get published. And that can distort facts and just leave everyone a little confused. So the best thing to do is to identify bias and make it as small as possible. You can perform good science in a biased environment. You can still have a well-designed, accurate study that has reproducible results. But there are cases where companies design flawed studies. And that's why it's important to communicate results and have other people perform the same experiments. Because if other people can replicate what you found, chances are there's less bias there. I guess this question's not going to load. Oh, there we go. Well, I think it said, think about weight and diet and how diet and weight loss companies advertise. Yes, they use bias. It's very obvious. If you've seen any commercial, it's very one-sided. How do you use skepticism to evaluate the data? So yeah, when looking at the ads, how would you evaluate the data? And here's a sample example answer. If you want to pause and check that out. But we are almost done. In summary, here's the video. If you guys want to check that out. But yeah, that was our first tutorial. I hope you found that somewhat helpful for me to walk you through or just talk to you about certain things. And yeah, that's it. I'll upload this so you have something to look at. And I will see you next time. Bye bye.